All right, here we're going to tackle the first application of integration, which could be called one of two different things. It could be called the mean value theorem for integrals. I never really call it the mean value theorem for integrals. We have a mean value theorem for derivatives. That's the one that says, hey, if I have a continuous and if I have a differentiable function, well then some interval a to b, right, I could find the secant slope between those 2 points. And what the mean value theorem for derivatives says is that, hey, somewhere in this interval, there's going to be a point where the tangent slope, the instantaneous rate of change, the derivative, matches the average rate of change. So the mean value theorem for derivatives is about the slopes matching. The mean value theorem for integrals is going to be about the areas matching. I never really call it mean value theorem for integrals. I always will just call it average value. But anyways, this average value, I think it's not super complicated. The formula for it is pretty easy. Let's go ahead and look into it. I have just some random function drawn. It looks like an inverted parabola. That's great. And we know the definite integral can tell me the area bounded by this weirdly shaped region. Now, what the average value theorem says is that there's some x value, right? There's some number that produces out this magical height. That height is the average height. We know sometimes the function is higher than the average, sometimes it's lower than average, but we know there's some average height to this function. And if I were to use this height, right, if I were to use this average height, and if I were to make a rectangle based on that average height, then the area of that kind of perfect rectangle would match the area of that weirdly shaped region. And it's this average height that's called the average value. I know it's kind of weird we call it average value. The average height is what we're looking for. The average value is kind of on average, what is the value of that function going to be over a specific interval, the value meaning the y-coordinate. Sometimes the function could be pretty big in terms of its value, sometimes it's kind of smaller, but we can find the average value or the average height of a function kind of based on this little process, right? The average value is a y-coordinate, it's a vertical distance upwards from 0, and if I use the average value or that average height, then the rectangle formed by using that average value and of course the width, the area of that rectangle is going to match the area of the region. Let's see if you kind of believe it, right? The area of this region looks like here we have this extra area, but it would fill in here and it would fill in here, right? The area of this weirdly shaped region is the same thing as the area of that perfect rectangle. Of course, if everything was drawn perfectly to scale, it would be. My diagrams may not be perfect, but they're pretty close, not to scale. Here we go. So let's get the formula. How do I calculate what this average height or what this average value is? It's a little bit weird. It's a y coordinate, right? It's a vertical height. That's what the average value is. And then there's some point on my interval where I'm going to hit it. That's kind of what the theorem says, right? If my function is continuous, then there exists some number c. There's some number in my interval so that the integration, that's the area, could be expressed by f of c, that's the height, and then b minus a, that's the width. Right? The f of c is the height of this perfect rectangle. B minus a is the width of this perfect rectangle. So I know the area of that perfect rectangle would be f of c times b minus a. Right? This is the area of the rectangle, and we know the definite integral gives us the area of that region. And if the area of the region and the area of the rectangle, if those are the same, then we can use the transitive property of equality that tells me, hey, the area of that region is the same as the area as that rectangle. So I could say, hey, if both of those two things, right, if that's the area of the region and that's the area of the rectangle, but the two areas are the same, then I could say the integration must be equal to f of c times b minus a. Now, what we want to get isolated, f of c is the average value. So here, think about it like this. If I take the area is the height times the width. If I wanted to get the height by itself, all I would need to do is take this b minus a, the width, and divide it over. So we can get this expression, f of c, that's the average value, the average height of a function over a specific interval. It's going to be 1 over b minus a, and then the integration from a to b. if I take the definite integral, that will give me the area. And if I take that area and divide it by the width, then that's going to tell me the height of the function on average over that interval. And that's what our formula is, right? Our average value, f of c, right? It's a y vertical distance. I take the integration of that region, that tells me the area. I take the area, divide it by the width. All right, the height equals area divided by the width. To find the area, you do the definite integral, divide by the width, which is your b minus a. Do not forget the b minus a. The common mistake here for students is that they're going to do the integration, and you're like, okay, that's good. But if you forget to divide by the width, you're going to get the wrong answer. So let's practice. Find the area, divide by the width. That's all we're doing. Here we go. I'll try to keep it on the screen. Oh, that's the wrong way. Let's go this way. It gives us this function, f of x equals 1 plus x squared. It says find, in the interval from -1 to 2, part A says find the average value of f on this given interval. Okay, so here we go. Average value, it's 1 over b minus a, so 2 minus -1, and then I need the integration from -1 to 2 of my function. You're just going to do the integration. That's going to tell me the area of the region. Then when I take the area and I divide by the width, that's going to tell me the height of the region. Let's say 2 minus -1, that's 3. And then let's do this integral. It would be x plus 1/3 x cubed. So I'm just integrating, just leaving this out in the front, integrating that term. Now let's plug it in. I'm going to just leave the 1/3 out in the front. I have the upper evaluation minus the lower evaluation. The upper comes from plugging in 2. So let's go ahead and plug in 2. So we get 2 plus 8/3 minus the lower evaluation from plugging in the -1. So we have -1 minus 1/3. Let's distribute this negative. I still have that 1/3 out in the front. I have 2 plus 8/3. That's going to be plus 1 plus 1/3. Let's go calculate what all this is. 2 plus 1 would be 3. 8/3 and 1/3 would be 9/3. So that's another 3. So we got 3, 3. So all this stuff inside the brackets, that's going to be 6. So the total area, right, if I were to graph this parabola, which we're about to in just a minute, the area of that parabola is going to be 6, divided by the width, and here that's going to tell me my average height, the average value of the function will be 2. Okay, now let's look at the part B. It says find the c. C is an x value. Find the c so that f of c will equal the average value. So I want to know, hey, where is f of c so that I'm going to get out 2, right? I'm going to set my function equal to that average value that we just calculated. So here we go. Take my function. You can use c or you can use x. I don't really care. 1 plus x squared equals 2. And then we can just take that function, set it equal to 2, and then solve it. Subtract the 1 over, I'll pick it up here. Subtract the 1 over, square root both sides. Don't forget your plus or minus. And so here we've got our two solutions. Now, one of those, right, we have x equals -1 and we have x equals 1. One of those is kind of more important than the other. This one happened to be the left endpoint of my interval. And if that happens, that's okay. Like, your endpoint can also potentially satisfy the theorem. But what the theorem says is there's going to be one number in my interval, right? See how it's a bracket, so it could be the endpoint. But really what we care mostly is that value that's in the middle of the interval. So both of these are right, but the one is kind of the more right answer. It's not really wrong to have the -1 also, but since that was an endpoint, we can include it, or if we were to just say, hey, x equals 1, that's fine. But 1 would be the x value that produces out the height of 2, which, the function isn't always the height of 2. It's not a constant horizontal line, but we're going to say on average, the height of that parabola over my specific interval, on average, the height is going to be 2. Let's look at the graph to check. Now, if you were to type this into the calculator, you could get a graph. And the graph is going to look something more or less like this. Now, my diagram is definitely not going to be to scale. I'm going to make it try to be fairly close. I know the intercept would be at 1. Then it would look something kind of more or less like this. Okay, so there's my function, and we would be trying to find the average value, right? So we'd say, hey, okay, the average height of this function on this interval, we have -1. Oh, I guess I needed to go all the way to 2, right? Let's see, 2. Oh, gosh, this diagram is definitely not going to be to scale. Oh, well. We'll say, hey, here we go. We've got this height over here on the right. We have this height over here on the left. And we're going to see if they are the same. All right, this diagram is like, it's really terrible. I'm going to fix it so that way we get something that looks a little bit more reasonable. Oh my gosh, that was like one of the worst graphs I've ever done. Let's redo it just because it's going to bother my OCD. Here we go. Parabola shifted up 1 unit. So it's going to be right here. Then if I go over 1, up 1 like this, then if I go to 2, 2 squared plus 1 would be 5. Okay, so there we go. So this is what the parabola is going to look like. And then we're really only caring about the interval from -1 to 2, right? So here's this weirdly shaped region. And what the average value was finding is we know this parabola always attains like different heights. Like sometimes the parabola really kind of exclude everything else. Sometimes the parabola is a little bit bigger. Sometimes the parabola is lower. But what we found for the average height, right, was 2, right? That was my average value. We think it was 2. So if I were to draw a rectangle using 2 as the height, would we believe that the area of that rectangle matches the area of the region? Do we believe that this region, or this little area that's in the region, do we believe that that would perfectly fill in the missing spot of the rectangle? And if we have diagrams that are a little bit more accurate, then the answer would be yes, that will be to scale. 2 is the average height of the parabola. Again, we're not really focusing on anything outside of the interval. Sometimes the parabola is lower than average. Sometimes the parabola is higher than average. But of course, that's what an average means, right? Sometimes you may be lower, sometimes you may be higher, but the average is kind of around that number in the middle. And if we were to take that rectangle formed by using the average value, 2, and of course the same interval width, then the area of this rectangle would match the area of this weirdly shaped region. So conceptually, I think it's a little bit weird, but actually practically finding it is pretty easy. All we do, remember the formula, you find the area. In order to find the area, you just do the definite integral. That's great. The area of this region, by the way, would have been 6. If you would have circled 6 as your answer, that wouldn't really make sense. But here we would take that area and then you divide it by the width. That's how you find the height, right? Take the area, divide it by the width, and then that's how we find average value. And our average value is a y vertical distance. And if you wanted to find the x that will produce it, it looked like we had the 2 different values, right? At 1, the y coordinate is 2, right? So 1 produces the average height, and then also -1, that y coordinate was up at 2. So both -1 happen to produce out the magic height, and 1 happens to produce out the magic height. But there's always going to be something in the middle of my interval, right? There's going to be some c value in the interval, so that if I take this and plug it into the function, the height at that point will be the average value, right? It will be the average height. That's a much better diagram than I was making that one is way too flat. That was really bad. But hopefully the second one I did was a little bit better. Okay, so let us go through and move on to the next one then, which instead of actually using the definite integral to get the area, now it says we're going to approximate what that average value is, because we're going to approximate the area not by doing the integral, but by doing a Riemann sum. And that Riemann sum will give us a guesstimation as for what that area is. Okay, but here we go. Remember, it says use the table of the values of a continuous function f are given below. Use a left Riemann sum with 3 subintervals and values from the table, and it wants to get the average value. I always like to write the formula just because I think it helps. Average value it's 1 over b minus a. Then you have your integration from a to b of your function. Okay, so for us, we're going to have the integration, we're going to have 17 minus 5, 1 over 17 minus 5. And then we'd have the integration from 5 to 17 of the function. And then it's this part right here, that part right there is what we're estimating with the Riemann sum. Okay, the 1 over 17 minus 5, that's fine, right? That's just 1/12, but it's all of this stuff that we're going to approximate by using a Riemann sum. Okay, so here we go. Let's go get the area of this region by approximating with the Riemann sum. The first interval would be from 5 to 9, which means you have a width of 4. The next one's going to be 9 to 12, which has a width of 3. The next one would be 12 to 17, a width of 5. Okay, so we don't have universal width. That's okay. That just means we have to focus on one interval at a time. If we have this first region from 5 to 9, the width of it will be 4. And then since we're doing a left Riemann sum, the height of that first rectangle would be 23. The second rectangle would be between 9 and 12. So the width is 3. And then for the left Riemann sum, you would be using the 29 for the height. And then for that third and final rectangle, the width will be 5. And then we'd be using the 36 for the height. Okay, so we would just use our Riemann sum to approximate what the area is, and then we would still take that area, divide by the width, and then here we go. We have the 1 over 12. If you were to add all this stuff together, just imagine me doing it in the calculator, we would get 359. And then 359 divided by 12. Oh, it's so close to dividing evenly, but it doesn't. 359 over 12. We can just leave that as the average value, or if you wanted to write it as a decimal, it'd be 29.917. Now, a common mistake for students to do is to just do the integration, and then you'll forget to divide by the width. And let's think about how nonsensical that would be. Okay, if you forgot the 1 over b minus a, right? If you just did the area, and you forgot to divide by the width. Okay, so we would have just had the area. That means I would have just had the integral, which means I would have just had the Riemann sum, which means my answer would have been 359. Okay, think about how silly that is. Think about where these coordinate points are on your coordinate grid, right? 5 is up at 23. Visualize where that would be, right? It's at a height of 23. The next one's at a height of 29. Then this one's at a height of 36. And then this one's at a height of 27, right? You're kind of visualizing where these up points are on your coordinate grid. So we got these y coordinates, in the 20s and, in the 30s. And you're going to try to tell me if you forgot to divide by the width. If you forgot to divide by the width, your answer would have been 359. If your coordinate points are in the 20s and 30s, how would your average be at 359? Like, that would be ridiculous. 359 would be so high above the 20s and 30s, it wouldn't even be on the same grid, right? It'd be way, way, way too big. However, if you were to take that area and divide it by the width, look, we get around 30, and around 30-ish seems reasonable, right? Because we were in the 20s and in the 30s, and so it makes sense that, hey, like this number, 29.917, like that seems fairly reasonable of an average out of these things. Now, you're not just going to add them and divide by 4, right? It's not a geometric average, it's a calculus average. So we're integrating and we're accumulating all of those values between 5 and 17. That's what integration does, right? It accumulates all infinitely many of those points. Then we divide by the width to kind of spread it out evenly. And so that's how we get the average value. The integration by itself is just the area. Do not forget to divide by the width. Usually, if you forget to divide by the width, you get an answer that's nonsense. If these are your data points, how is your average 359? That wouldn't even make sense, right? Typically, if you forget to divide by the width, like, your answer will be noticeably terrible. So just be careful. The formula, 1 over b minus a, then you do the integration from a to b. Okay, don't forget the b minus a part. Here we go, a couple more examples, and then we'll be done. A study suggests that between the hours of 1 p.m. and 4 p.m. on a normal weekday, the speed of traffic on a certain freeway exit is modeled by this formula, S of t. So that's your speed formula, where the speed is measured in kilometers per hour and t is the number of hours past noon. compute the average speed of the traffic between the hours of 1 and 4. First thing I always do, right? It says the number of hours past noon. So that's time equals 1 and that's time equals 4. How lovely. Now it gives us the speed function and it wants the average speed. Okay. Average speed, that's just the average value of the speed function, right? That makes sense, hopefully. Average speed, that's the average value of your speed function. And specifically, it wanted 1 to 4. So we're going to have to use the time interval 1 to 4, which means we're going to have 1 over 4 minus 1. Don't forget to divide by the width. And then I'll have the integration from 1 to 4 of that s of t function. If I take the average value of your speed function, that will give you the average speed. Could I integrate this by hand? Yes, right? It's a pretty easy polynomial. I could integrate it. Could I plug in 4? Could I plug in 1 by hand? Yes, those are pretty easy, manageable numbers. Could I also divide by 3? Yes. I could do all of this by hand if I really needed to. If push came to shove, I could, but I'm going to just not do it just for the sake of time. This ends up being, of course, 1/3. If you were to math 9 it, right, so we'll say math 9 with our graphing data calculator, you would end up getting 393 over 2. Okay, so you're like, okay, that's pretty big, right? If you didn't remember to do your 1 over b minus a, right, you get 393, so you get almost 200 kilometers per hour. That would be a very, very, very fast freeway exit. That would be scary, okay? But luckily, we did have to divide it by 3, so it's going to be a little bit more reasonable. If you only do the area, typically your answer is way too big. But we do the area, divide it by the width. That's how we get the height. Okay, so here we go. Remember, we just math 9 to get that value. Could have done it by hand, but I didn't want to. So then here we would just simplify it, and we would get 131 over 2, which equals 65.5, and then the units, what's it, kilometers per hour. So kilometers per hour. That seems a little bit more reasonable, right? If you forgot to divide by 3, that's a really big kilometers per hour. You're going way too fast. But to find the average speed, you could do the average value of the speed function. So you take that speed function, integrate it, and then don't forget to divide by the width. Okay, next one. This one's one of my least favorite ones, but it's okay. It says, suppose that during a typical winter day in Minneapolis, the temperature in degrees Celsius X hours after midnight is shown in the figure below. Use a midpoint Riemann sum with 4 equal subintervals to approximate the average temperature over the time period from 4 a.m. to 8 p.m. And then part B, use the answer to A to estimate the time when the average temperature occurred. Okay, so let's go for it. First things first, let's find the average value. And it says, I know, to get the average temperature, that's too many little lines. I could do the average value of the temperature function. Like, we know that average temperature is the average value of the temperature function. This is the temperature function. And then let's go figure out what our t-values are, right? It's the number of hours past or after midnight. So 4 a.m. is going to correspond to t equals 4. 8 p.m., think about military time, that's going to be t equals 20, right? It's not 4 to 8 because it's not 4 a.m. to 8 a.m. Just be careful with how your units of time are measured with respect to, right? It's hours since midnight. So 4 a.m. is 4, 8 p.m. is 20. So I'm going to have to do 1 over 20 minus 4, and then I'm going to need to get the integration from 4 to 20. I don't know. This temperature function is not labeled, so we'll just leave it whenever the integration simple. Now, we're going to have to approximate this. I have the 1 over 16. I'm just going to leave that sucker out in the front, and then we'll do all this stuff, right? All this stuff right here is going to come from the Riemann sum. And it says a midpoint Riemann sum with 4 equal subintervals. So let's do this little Riemann sum, and the Riemann sum will give us the estimation for this. Once I have that area, we'll divide it by the 16 to get that average height. right? We can see these temperatures are really cold, right? Sometimes it's super cold, sometimes it cracks right above zero. So we're kind of visualizing where we think that average is going to be. It's probably not super close to the bottom nor super close to the top. We're trying to visualize like where we think that average, that kind of middle-ish number would be. And we can kind of start seeing, hey, it's probably somewhere in like this area-ish, right? But we're going to calculate where that height of that average is by doing this formula. All right, so let's think about it. 4 equal subintervals. If the interval is from 4 to 20 in total, if I'm going to take it, right, that total width is 16. 16 divided by 4, that's 4. That means my intervals will be 4 to 8. Then it'd be 8 to 12. Then it would be 12 to 16. Then it would be 16 to 20, right? Those are your intervals that we're going to use for this Riemann sum. So here we go. There's 4. Here's 8. 12, 16, and 20. So we've got these little intervals, 4 to 8, that's the first one. Then 8 to 12, second one. 12 to 16, that's the third one. And then the last one, 16 to 20. And we're going to use the midpoint value for the height of each rectangle. All right, so the midpoint, this first interval is from 4 to 8. The midpoint of it would be 6. So I have to figure out where is the function when time equals 6. It looks like it's about here. I would use that midpoint's y value as the height of my rectangle. And then I'd be like, okay, there, look, there we got the area of that first rectangle. It's going to be negative, that's okay. And then we'll just kind of guesstimate where that height is. But the area, or sorry, the width of it, right, all the widths of these rectangles is going to be 4. So I'm going to have that universal width factored out. And then the height of this first rectangle, let's see, that's 2, that's 4, so that would be 6. So I'm going to call this height, I don't know, -5, right? It's a guesstimation. We're going to guess that this vertical height right here, we're going to guess that it was about -5. It's pretty close, right? It may not be perfectly to scale. That's okay. The height of that first rectangle is -5. Okay, second rectangle is the interval from 8 to 12, which means 10 would be the midpoint, which means I have to figure out what's the y-coordinate when x is 10. Here's 10. Here's about where that point is. I'm going to just draw that horizontal line. So there's my little second rectangle, and I'm going to guesstimate that the height, f of 10, I'm going to guesstimate it that it's 1. So the height of my second rectangle is 1. The third rectangle between 12 and 16, the midpoint of it would be 14. I'm just going to say that one looks pretty close to this line, so I'm going to say, hey, that one's just up at 2. So I'm going to say this area, or that height of that second rectangle, I'm just going to guesstimate it 2. If you want to use 1.9, that's fine. You probably have a slightly better estimate, but 2 is easier than 1.9, so I'm going to use 2. And then we have this last interval from 16 to 20. The midpoint would be 18. So I need to figure out, here's 18. Here's that y-coordinate when t is 18. And then I'm going to just guesstimate that that y-coordinate is -1. So we had a midpoint Riemann sum. Again, we kind of estimated what the heights of all those midpoints were. That's okay. But we had the heights, we have the universal width factored out, and then we can calculate all this stuff up. Let's see, the 4 over the 16, I'm going to reduce it, right? So that's just 1/4. If I were to add all this stuff, those would cancel. We have the -5 and the +2, so that's -3. So we're going to end up figuring out that this average temperature is going to be about -3/4. Let's see, what units do we have? Degrees Celsius. That's what we can kind of tell our average temperature is. Now, if I were to actually graph that, right? Ooh, I shouldn't have done the rectangles so heavy. I'm going to erase them. Good thing I did them in pencil. Okay, so the next thing we're going to do is we're going to take that average and we're going to draw a horizontal line at the average. So let's go for it. We're going to draw a horizontal line with the height of 3/4. I mean, keep it a little bit more level. Okay, there we go. 3/4. Here's 2. Here's 1. So it would be something. Oh, it's negative. So here's -2. So 3/4 would be, I don't know, somewhere around here-ish, right? Your horizontal line may not be the precise same as mine, but -3/4. Right, this is -2, so it shouldn't quite be the halfway, but it's a little bit less than it. And I can tell that function is going to hit it right here. And that function is going to hit it again right here. So it looks like there's two time values where your temperature is going to be the average, right? Where is the temperature going to be the average? Or what time does the average temperature occur? It would be the t values where your function intersects with your horizontal average. That's 8. That's 10. So I'm going to guesstimate that is around time equals 9. That's 16, that's 18, so I'm going to guesstimate that that's around time equals 17. Just based on how you draw a graph, it may be slightly different. Well, this was the work for A. Now we got the part for B. So we had time equals 9 and time equals 17. But of course, I wouldn't want to end it with 9 and 17. We'd want to change it back to like AM times and PM times. So therefore, we would say approximately 9 a.m. and then approximately, I see military time, that would be 5 p.m. Those are approximately going to be the times when we hit the average. Remember, there's lots of estimating involved. We had to estimate what the y-coordinates were. We had to estimate that to get the Riemann sum, which was itself an approximation. Then I had to draw the horizontal line. That's going to have some error, right? And then we're seeing where those intersection points are. So there's lots of error involved here. But at the end, everyone should get something fairly close to negative 3/4. If you were to use slightly different values, your answer may be slightly off, but it should be fairly close to negative 3/4. And then wherever your horizontal line is, your time values to hit it should be probably fairly close to 9 a.m. and 5 p.m. If you had 8 and 4, or if you had 8 and 6, that's probably okay, but it should be probably fairly close. Okay, let's keep going. One more example with average value, and then we're done. Okay, here we go. Find the average value of the function on the given interval without integrating. This says hint. Graph and use geometry areas to get the geometry formulas to get the area. Okay, well, let's graph this thing first. Here we go. We've got 3 minus x. So let's see, if I were to plug in -1, 3 minus -1, it's going to be up at 4. So this point will be up at 1, 2, 3, 4. The intercept is 3. That's easy. Then it's going to go all the way to 3. 3 minus 3 would be 0. So here, this little function is going to look like this. Great. And then if I were to graph this, let's see, if I plug in 3, 2 times 3 would be 6. 6 minus 6 is 0. Okay, it is continuous. If I were to plug in 3 to this piece and 3 to this piece, you both get 0. So they both are going to intersect at that x-intercept. So that's great. And then if I plug in 6, let's see, 2 times 6 would be 12. 12 minus 6 should be 6. So this should be at a height of 6. It's going to go up 2 over 1. So this is going to be at 2. Guesstimate it. That's going to be 2 more, 4. Then that's going to be over here at, see, 2, 4. Oh my gosh, too many lines. 1, 2, 3, 4, 5, 6. I'm getting too confused. There we go. About there. So that's at a height of 2. That's at a height of 4. That's at a height of 6. Okay, so I know, right, I can see what this graph is going to look like. I know I could use geometry to get this area. I could also integrate, right? If I were to integrate this function, 3 minus x, from -1 to 3, like I could, right? This definite integral would tell me this area, but it specifically told me do it without integrating, right? That doesn't mean do it in your head, because you're still integrating. You're just doing it in your head. Without integrating means, hey, don't use calculus like at all. So like we're going to use some geometry instead. But I know, like, hey, this area on the left would be equal to that integral, and then this area on the right, it would be the integration from 3 to 6 of your second function, 2x minus 6. Okay, so I know, right, my formula for average value, it would be 1 over b minus a, so 6 minus -1. Then I would have the integration from 1 to 6 of your function. Since this is a piecewise, you'd have to split it out. You'd have the 1/7, and then I'd have -1 to 3 of the first part, plus 3 to 6 of the second part. I know I could do those, right? Both of those are easy, right? I could integrate those. 3x minus 1/2 x squared, easy. Plugging in, easy. X squared minus 6x, easy. Plugging in the 6 and 3, easy, right? I could absolutely do this the calculus way, but instead, we're just going to do geometry, right? This will give us this region's area, which is just a triangle. So we can do 1/2. The base is going to be 4, and then the height was also 4. So you could do the calculus, but I'm going to use geometry because it's faster. Then here it's going to be 1/2. The base was 3, and the height was 6, right? This was 3, this was 6, this was 4, and then this was 4. So it says without integrating. That means don't do the calculus. Don't even do it in your head because that's still doing it. But it's using the geometry instead. So here we go. 4 times 4 would be 16 divided by 2. So that's 8 plus, let's see, that's 18 divided by 2. So that's 9. So you're like, okay, Mr. Bell, 17. And you're like, okay, that's not right because you dropped something, or maybe more likely you may never put that 1 over b minus a to begin with. If all you do is the integration, remember what you're doing conceptually is finding the area. That's great. The area of that region is 17. That's not the average value, right? If you're trying to tell me that 17 is the answer, right? If 17 is the average height, how is the height going to be 17? Like the biggest it ever gets up to is 6. If you tried to tell me the average is up here at 17, like that would be stupid, right? That would be really, really, really dumb. Your function only even exists, right? In this piece and then this piece. So we're kind of thinking the average should be something kind of more in the middle-ish, right? The average shouldn't be up here at 17. So usually if you forget that 1 over b minus a, right, your answer is going to be pretty bad. But here, the 17 over 7, that's a little bit more reasonable. If you were to convert this into a decimal, you would get about 2.4, about 2.429, I think. So it's about 2.5. Let's try to look at it, right? If I were to draw a rectangle with the height of about 2.5, let's see if we kind of believe that it's that magic perfect rectangle. If I were to use the average value, so if I were to use this about 2.4 whatever, if I were to use that height for my rectangle, do you believe that the area of this rectangle matches the area of this total collective region? Well, here that would fill in part of it. This would fill in the rest. Yes, that does seem like a fairly decent average. Sometimes the function's higher than average. Sometimes the function's lower than average. But what we are calculating when we do the integration, divide it by the width, what we're doing is calculating on average what the height of that function is. We know it doesn't always have to be the average, right? It's not linear function. Well, at least it's not a horizontal. Those are both linear functions, but it's not a horizontal linear function. But we can kind of guesstimate where that average, and we can find where that average is by using this theorem called the average value, the mean value theorem for integrals. Remember, the mean value theorem for derivatives was all about the slopes matching. Hey, somewhere in the middle, the tangent slope is going to match the secant slope. The mean value theorem for integrals is about the area matching. Somewhere in the middle, right, kind of this point right here, and this point right here, right, those would be your C values. Those are going to be your numbers in your interval that produce out and that hit the average. Okay, so average value, it's finding the height on average of that function over that interval. And to find the height, you take the area, divide it by the width. Hopefully that makes sense.